Imagine looking up at the night sky and realizing something deeply unsettling. Every galaxy you see, every cluster, every massive structure in the universe is moving. Not randomly, not gently, but being pulled toward something we cannot see, something we cannot fully measure, something we still don't understand. In the 1970s, astronomers studying galaxy motions discovered something strange. Galaxies weren't just moving away due to expansion, they were drifting sideways, deviating from where they should be going. And when scientists traced those motions backward, they all pointed in roughly the same direction, toward a region of space hidden behind our own galaxy. A region so obscured, so difficult to observe, that for decades it remained almost invisible. But the motion was undeniable. Hundreds of galaxies, then thousands, all accelerating toward a single gravitational source. And here's the disturbing part. That source is so massive, so enormous, that it's influencing galaxies hundreds of millions of light years away. We gave it a name, the Great Attractor. But naming something doesn't mean understanding it, because when we finally started mapping that region more clearly, we realized something even stranger. What's pulling these galaxies might not fully exist within the structure of the known universe the way we expect. And that raises a question that physicists still struggle with today. What exactly is pulling galaxies, and why is it so powerful? To understand why this is so strange, we need to start with something you already know, but not in the way you've probably thought about it. The universe is expanding. This idea comes from observations made by Edwin Hubble in the 1920s. He discovered that distant galaxies are moving away from us, and the farther they are, the faster they recede. This relationship is known as Hubble's law, and it tells us something fundamental. Space itself is stretching. Galaxies are not flying through space like bullets. Instead, the fabric of space between them is expanding, carrying them apart. If this were the only effect in the universe, then galaxy motion would be simple. Every galaxy moves away from every other galaxy. Motion is smooth, predictable, no preferred direction. But that's not what we observe. When astronomers measure the motion of galaxies carefully, they find something called peculiar velocity. This is the motion of a galaxy after subtracting the expansion of the universe. And this is where things get interesting. Because galaxies aren't just moving apart, they're also falling into clusters, orbiting massive structures, being pulled by gravitational forces. Gravity still matters. Even in an expanding universe, matter clumps together due to gravity. Over billions of years, this leads to the formation of galaxy clusters, superclusters, filaments, and voids. This large-scale structure is often called the cosmic web. And within this web, galaxies don't just move outward, they move toward mass. This is completely expected. If there is a massive cluster nearby, galaxies will accelerate toward it. The stronger the mass, the stronger the pull. So far, nothing unusual. But now consider this. When scientists mapped the motion of our own galaxy, the Milky Way, they found that it is moving at roughly 600 kilometers per second relative to the cosmic microwave background. That's not a small drift. That's a huge velocity. And it's not random, it's directed. Which means something is pulling us, too. In the 1970s and 1980s, astronomers began systematically measuring the velocities of galaxies across large regions of space. Two key researchers, Donald Lynden Bell and his collaborators, analyzed galaxy motions and noticed a pattern that shouldn't exist if the universe were perfectly uniform. Galaxies across vast distances were not just moving away from each other, they were flowing toward a specific region in the sky. This motion became known as a bulk flow. Instead of random local movements, entire groups of galaxies spanning hundreds of millions of light years were drifting together in the same direction. That direction pointed toward a region in the constellation of Centaurus. But there was a problem. That region lies behind what astronomers call the zone of avoidance. This is an area of the sky obscured by the dense dust and stars of our own galaxy, the Milky Way. In visible light, it's almost impossible to see what's behind it. So astronomers were faced with a paradox. Galaxies were clearly being pulled in a specific direction, but the source of that pull was hidden. Using radio waves and infrared observations, scientists slowly began to peer through the dust. What they found was not a single object, but an enormous concentration of mass. Clusters of galaxies, superclusters, all merging into something larger. This structure became known as the Great Attractor. Estimates suggest it has a mass equivalent to tens of thousands of galaxies, and it lies roughly 150 to 250 million light-years away. At that scale, its gravitational influence is enormous. But here's where things become unsettling. Even after accounting for the Great Attractor, the observed motion of galaxies still doesn't fully match predictions. There are residual velocities, unexplained motion, as if something even larger, something beyond the Great Attractor, is also influencing the flow. Some studies point toward an even bigger structure called the Shapley supercluster. Others suggest the motion extends across scales so large that it challenges our assumptions about uniformity in the universe. And this brings us to a deeper problem in physics. The universe, on large scales, is supposed to be isotropic and homogeneous, the same in all directions. This is a core assumption of modern cosmology, embedded in models based on general relativity. But large-scale flows like this hinted something else, a preferred direction, a gravitational influence that stretches across distances so vast that it begins to question whether our current models fully describe reality. To move forward, we need to understand how structures this large even form in the first place. Because the existence of something like the Great Attractor is not by itself impossible. In fact, modern cosmology predicts structure formation through a process driven by tiny fluctuations in the early universe. Shortly after the Big Bang, the universe was almost perfectly uniform, but not completely. There were minute variations in density, on the order of 1 part in 100,000. These fluctuations are preserved in the radiation we observe today as the cosmic microwave background. Over billions of years, gravity amplified these small differences. Regions that were slightly denser attracted more matter. As they accumulated mass, their gravitational pull increased, drawing in even more matter. This is known as gravitational instability, and it's the foundation of how galaxies, clusters, and superclusters formed. But there's a complication. If we calculate how fast ordinary matter, protons, neutrons, electrons, can clump together under gravity, it's too slow to explain the structures we see today. The universe simply hasn't had enough time. This is where the concept of dark matter becomes essential. Dark matter does not emit or absorb light. It doesn't interact electromagnetically, but it does have mass, and therefore it exerts gravitational influence. In current models, dark matter makes up about 85% of the total matter in the universe. Because it doesn't interact with radiation, it began collapsing into structures earlier than normal matter. It formed a kind of invisible scaffolding, a gravitational framework into which ordinary matter later fell. This is how the cosmic web emerges. Dense nodes, galaxy clusters; filaments, connecting structures; voids, vast, empty regions. The Great Attractor is located at one of these dense nodes. So at first glance, everything seems consistent. A large concentration of matter pulls galaxies inward. That's exactly what gravity predicts. But now we have to ask a more precise question. Is the Great Attractor massive enough to explain the observed motion? When astronomers calculate gravitational influence, they don't just look at position, they look at velocity fields. In simple terms, they map how galaxies are moving through space and compare that motion to what would be expected from known mass distributions. If the Great Attractor were the only dominant structure in that region, then galaxy velocities should converge toward it in a predictable way. But they don't. There's a mismatch. Some galaxies are moving faster than expected. Others are drifting in directions that don't align perfectly with the Great Attractor's gravitational pull. This suggests that the Great Attractor is not the full story. Beyond it lies an even more massive region known as the Shapley supercluster, one of the largest known concentrations of galaxies in the nearby universe. It contains thousands of galaxies, far more than typical clusters. Its gravitational influence extends across enormous distances. When scientists include the mass of the Shapley supercluster in their models, the observed motion of galaxies becomes more consistent, but still not perfectly explained. There are still residual flows. This has led to the concept of large-scale bulk flow, where entire regions of space, spanning hundreds of millions of light-years, move coherently in one direction. This is not just local gravity. This is motion on scales approaching the limits of what we expect the observable universe to behave like in a uniform way. And here's the tension. According to the standard cosmological model, often called lambda CDM, the universe should become increasingly uniform at larger scales. Fluctuations should average out. There should be no large preferred direction when you zoom out far enough. But bulk flows suggest otherwise. They hint that structure and motion may persist on scales larger than expected. And that raises a deeper possibility. Either our measurements are incomplete, or our model of the universe is. To understand how serious this problem is, we need to connect galaxy motion to one of the most important observational tools in cosmology, the cosmic reference frame defined by the cosmic microwave background. The CMB is the afterglow of the early universe emitted about 380,000 years after the Big Bang. It fills all of space and provides a nearly perfect reference for measuring motion. If we were completely at rest relative to the universe as a whole, the CMB would appear uniform in all directions. But it doesn't. Instead, we observe a dipole anisotropy, a slight temperature difference across the sky. One direction appears slightly hotter, the opposite slightly cooler. This is interpreted as a Doppler effect caused by our motion through space. From this, scientists calculate that the Milky Way, along with its local group of galaxies, is moving about 600 kilometers per second relative to the CMB. This motion is not due to cosmic expansion. It is due to gravitational attraction. So, now we can connect the pieces. The cosmic microwave background gives us a universal rest frame. Our galaxy is moving relative to it. That motion must be caused by gravitational forces. And when we trace that motion through the large-scale structure of the universe, it aligns, roughly, with the direction of the Great Attractor and beyond. But here's where things become subtle. If all motion could be explained by nearby structures, then as we map more distant regions, the velocity field should converge to zero relative motion at sufficiently large scales. In other words, beyond a certain distance, the universe should look statistically the same in all directions. But some studies suggest that even at very large scales, motion persists. There are indications, still debated, that galaxy clusters separated by over 1 billion light-years may share a coherent flow. If true, this challenges a foundational assumption in cosmology, that the universe is isotropic and homogeneous on the largest scales. And if that assumption weakens, then many of our equations, derived from general relativity under those conditions, may need to be re-examined. At the core of modern cosmology lies a framework that has been extraordinarily successful, the LCDM model. L represents the cosmological constant associated with dark energy, and CDM stands for cold dark matter. This model explains the expansion history of the universe, the formation of large-scale structure, the statistical properties of the cosmic microwave background. It does so using a relatively small set of parameters, and remarkably, it matches observations with high precision. But LCDM relies on a crucial assumption, that when averaged over sufficiently large scales, the universe is homogeneous and isotropic. This assumption is not just philosophical, it's mathematical. It allows the use of simplified solutions to general relativity, specifically the Friedmann-Lemaitre-Robertson-Walker metric. Without this assumption, the equations become far more complex, and many predictions lose their clarity. Now consider what large-scale bulk flows imply. If galaxies across hundreds of millions or even billions of light-years are moving coherently in a preferred direction, then the universe may not be isotropic at those scales. This doesn't immediately break LCDM, but it strains it. Because in LCDM, velocity fields arise from initial density fluctuations seated in the early universe. These fluctuations follow a statistical distribution that should, on large scales, average out. So while local flows are expected, very large coherent flows are increasingly unlikely. This is where the concept of cosmic variance comes in. Even in a perfectly isotropic universe, observers in different locations may measure slightly different properties due to random fluctuations. But there's a limit to how large these deviations should be. Some observed bulk flows appear to approach or exceed those limits. And that opens the door to a more radical question. Are we seeing a rare statistical fluctuation or evidence of something missing in the model? One of the more controversial ideas proposed to explain these observations is something called dark flow. The term emerged from studies of galaxy clusters using the kinematic Sunyaev-Zeldovich effect, a subtle distortion of the cosmic microwave background caused by the motion of galaxy clusters through the cosmic rest frame. When CMB photons pass through a cluster of galaxies, they interact with high-energy electrons in the hot gas. If the cluster is moving, this interaction slightly shifts the energy of the photons. By measuring this shift across many clusters, scientists can estimate their motion relative to the CMB. In the late 2000s, analyses suggested that hundreds of galaxy clusters might be moving together in a coherent flow extending over distances up to 1 billion light-years or more. Even more intriguing, this flow appeared to be aligned in a consistent direction, one that didn't diminish with distance as expected. If confirmed, this would be extremely difficult to reconcile with LCDM, because such a large-scale flow would imply a gravitational influence extending beyond the observable structures we can map. This led to a provocative interpretation, that the motion might be influenced by structures beyond the observable universe. Not outside the universe in a simple spatial sense, but beyond the region from which light has had time to reach us since the Big Bang. In other words, regions we cannot see may still influence what we observe. However, this idea is highly debated. Subsequent analyses using data from missions like Planck satellite have challenged the statistical significance of dark flow. Some studies find weaker signals or none at all. Others argue that measurement uncertainties, especially in isolating the kinematic Sunyaev-Zeldovich effect, are too large to support strong conclusions. So we are left in a state that is common in frontier physics. Evidence that is suggestive but not definitive, models that are successful but not complete, observations that can be interpreted in multiple ways. And yet, even if dark flow as originally proposed is not real, the underlying issue remains. Galaxy motions are complex and not perfectly explained. To push further, we need to examine an even deeper layer, the initial conditions of the universe itself. In LCDM, the large-scale structure of the universe originates from quantum fluctuations that were stretched to cosmic scales during a period of rapid expansion known as cosmic inflation. Inflation predicts that these fluctuations should be nearly scale invariant, Gaussian, random with no preferred direction, and statistically isotropic. These predictions are strongly supported by measurements of the cosmic microwave background. But not perfectly. There are anomalies. For example, slight asymmetries in temperature fluctuations, large-scale alignments sometimes referred to as the axis of evil, and hemispherical power differences. Individually, these anomalies are not statistically overwhelming, but collectively they raise the possibility that the early universe may not have been perfectly isotropic. If there were even a small preferred direction imprinted during inflation, it could, in principle, influence structure formation on very large scales. This would provide a natural explanation for coherent flows without requiring unknown structures or forces. But this idea comes with its own challenges. Inflation is designed to erase initial asymmetries, smoothing the universe to extreme uniformity. To preserve a preferred direction, inflation itself would need to be modified. This leads to alternative models: anisotropic inflation, vector field-driven inflation, and multi-field scenarios with directional dependence. These models are mathematically consistent, but they introduce additional parameters and complexities. And so far, the observational evidence is not strong enough to clearly favor them over the standard picture. Still, they remain an active area of research, because if the universe does have a subtle directional bias, then what we are seeing in galaxy motion may not be an anomaly at all, but a reflection of the universe's deepest initial conditions. Up to this point, we've been describing galaxy motion as if something is pulling them. But in physics, especially in large-scale cosmology, that language can be misleading. Galaxies are not being pulled in isolation. They're moving within a gravitational potential field, a continuous landscape shaped by the distribution of matter and energy across the universe. Instead of thinking in terms of forces acting at a distance, it is more accurate, especially within general relativity, to think in terms of curved space-time. Mass and energy determine the geometry of space-time, and objects follow paths, geodesics, within that geometry. So when we observe galaxies accelerating in a particular direction, what we are really seeing is motion along gradients in this gravitational potential. In practice, cosmologists reconstruct this potential using galaxy surveys. They measure positions of galaxies, redshifts to estimate distance and expansion, and kinematic Sunyaev-Zeldovich effect. From this, they build maps of the density field and infer the underlying gravitational landscape. One important result from these reconstructions is that motion is not just driven by over-dense regions like clusters and superclusters, but also by under-dense regions known as voids. This introduces a subtle but critical point. Galaxies are not just pulled by massive structures. They are also effectively pushed away from voids. Cosmic voids are vast regions of space with extremely low matter density. They can span tens to hundreds of millions of light years. At first glance, they seem unimportant, empty regions with little influence. But dynamically, they play a major role. In a region with very little mass, there's less gravitational pull inward. Surrounding regions with higher density exert stronger gravitational attraction, so matter flows away from voids toward denser monadics. This creates a repulsive effect, not because voids exert a force, but because of the imbalance in gravitational pull. In large-scale velocity maps, this effect is clearly visible. Galaxies tend to stream out of voids and into filaments and clusters. So when we observe a coherent motion of galaxies in one direction, part of that motion may be explained not only by attraction toward massive structures like the Great Attractor, but also by expansion away from nearby voids. This reframes the original question. Instead of asking, what is pulling galaxies, we should ask, what is the combined effect of all gravitational gradients, both overdense and underdense, regions on galaxy motion? When this is taken into account, some of the observed motion becomes easier to explain. However, not all of it. Even with detailed modeling of known superclusters, void distributions, dark matter density fields, there remain discrepancies between predicted and observed velocities. These discrepancies are not enormous, but they are persistent, and in precision cosmology, small mismatches matter. To quantify these mismatches, cosmologists use statistical tools that compare observed velocity fields with those predicted by LCDM simulations. These simulations start from initial conditions consistent with the cosmic microwave background and evolve structure forward in time using gravity and dark matter dynamics. The result is a synthetic universe that can be directly compared with observations. In most respects, the agreement is excellent. The distribution of galaxies, the clustering patterns, and the general scale of structures all match remarkably well. But velocity fields are more sensitive. They respond directly to gradients in the gravitational potential, which means they can reveal subtle inconsistencies. Some surveys have reported bulk flows larger than expected within the LCDM framework. Others find results consistent with the model, but with large uncertainties. This inconsistency across measurements highlights an important limitation. Measuring galaxy velocities is extremely difficult. Unlike redshift, which is relatively straightforward to measure, peculiar velocity requires independent distance estimates. These are obtained using methods such as Type 1a supernovae as standard candles, the Tully-Fisher relation for spiral galaxies, and the fundamental plane for elliptical galaxies. Each method carries its own uncertainties. Errors in distance measurements propagate directly into velocity estimates. As a result, distinguishing between a real physical anomaly and a statistical or systematic error is challenging. This is why the question of large-scale flows remains open, not because we lack theories, but because the data is at the edge of what we can measure reliably. At this stage, we've reached a deeper layer of the problem. We understand how structure forms. We understand how gravity drives motion. We can model the universe with high precision. And yet, there are still small but persistent gaps between theory and observation. These gaps are where new physics, if it exists, would begin to appear. So far, everything we've discussed assumes that gravity behaves exactly as described by general relativity on all scales. This assumption is central. Every reconstruction of galaxy motion, every simulation of large-scale structure, and every interpretation of bulk flow depends on it. But there is a fundamental limitation. General relativity has been tested with extremely high precision within the solar system and on galactic scales. But on scales of hundreds of millions to billions of light-years, direct tests are far more limited. This opens a legitimate scientific question. Does gravity behave exactly the same way on the largest scales of the universe? If even slight deviations exist, they could alter how structures grow and how galaxies move within the cosmic web. One class of alternatives involves modifications to the gravitational field equations. Instead of changing matter content, these models modify how space-time curvature responds to energy and momentum. Examples include F of R gravity models, scalar tensor theories, and massive gravity scenarios. In these frameworks, the relationship between mass and gravitational influence is slightly altered. This can lead to different growth rates of structure, changes in the depth and shape of gravitational potential wells, altered velocity fields for galaxies. In some cases, these models can produce enhanced large-scale flows, potentially accounting for observations that appear too strong under LCDM. However, there is a constraint. Any alternative theory must still reproduce the precise observations of the cosmic microwave background, gravitational lensing, and galaxy clustering statistics. This makes the problem extremely difficult. Because LCDM is not just approximately correct, it is quantitatively accurate across many independent datasets. So any modification must be subtle enough to preserve these successes while still addressing anomalies in velocity fields. This is why no alternative theory has yet replaced it, but the possibility remains open. Another layer of complexity comes from the role of dark energy. In standard cosmology, dark energy is treated as a uniform component that drives the accelerated expansion of the universe. It does not cluster like matter. It does not form structures. And importantly, it is not expected to directly influence local galaxy motion beyond its effect on the expansion rate. But this assumption depends on dark energy being perfectly uniform. If even slight spatial variations or interacts weakly with matter, then its effects could extend beyond simple expansion. Some theoretical models explore this possibility. Dynamical dark energy, quintessence fields, coupled dark energy dark matter models, inhomogeneous dark energy distributions. In these scenarios, dark energy could contribute to gradients in the large-scale potential, subtly affecting motion. The effects would be small, but on very large scales, they could accumulate. This could manifest as slight deviations in velocity fields, anomalous bulk flows, directional asymmetries. However, observational constraints are tight. Data from supernovae, the cosmic microwave background, and large-scale structure surveys all strongly support a model where dark energy is close to a cosmological constant. So while these alternatives are actively studied, there is no clear evidence yet that dark energy behaves in a way that would explain large-scale galaxy flows. Still, the key point remains. Even small deviations in fundamental components of the universe can produce measurable effects at large scales. At this stage, it becomes necessary to question something even more foundational. Not just how matter and energy behave, but how we define the observable universe itself. When we say galaxies are being pulled toward a region, we are describing motion within our observable horizon, the region of space from which light has had time to reach us since the Big Bang. But beyond this horizon, there may exist additional structures, density variations, gravitational influences. These regions are not directly observable. We cannot see them, we cannot map them. But according to general relativity, their gravitational influence does not abruptly stop at the edge of what we can observe. Gravity propagates at the speed of light, so only regions within our past light cone can currently affect us. However, the large-scale structure we observe today was influenced by initial conditions that extend beyond our current horizon. This leads to a subtle but important point. The universe may be larger and more structured than the portion we can observe. If there are large-scale density gradients extending beyond our observable region, they could, in principle, produce coherent motion within it. This idea does not require exotic physics. It only requires that the universe is not perfectly uniform on scales larger than we can see. In such a scenario, what appears to us as a preferred direction or anomalous flow could simply be the local manifestation of a much larger structure. But this explanation has limits. Inflation theory predicts that the observable universe should be a tiny, highly uniform patch of a much larger cosmos. Large gradients across our observable region would be unexpected. So again, we arrive at a tension. The simplest models predict uniformity. Some observations hint at large-scale coherence, and the difference between the two is small, but significant. To refine these ideas further, cosmologists increasingly rely on high-resolution simulations. These simulations incorporate dark matter dynamics, gas physics, star formation processes, feedback from supernovae and black holes. They evolve billions of particles over cosmic time, producing detailed models of structure formation. Within these simulations, velocity fields emerge naturally from gravitational interactions. By comparing simulated velocity distributions with observed ones, scientists can test whether current physics is sufficient. In most cases, simulations reproduce the amplitude of typical galaxy velocities, the distribution of clusters and voids, the statistical properties of motion. But rare events, extreme bulk flows, are more difficult to assess because they depend on low probability fluctuations. In a universe as large as ours, rare events can occur. The question is whether what we observe falls within those probabilities. Some analyses suggest that large bulk flows are unlikely but not impossible within LCDM. Others argue that observational uncertainties are large enough that no real discrepancy exists. This is where the field currently stands, not with a clear contradiction, but with a region of uncertainty at the edge of measurement and theory. At the deepest level, the question of what is pulling galaxies becomes a question about how structure, motion, and space-time are connected. In an expanding universe, motion is not simply superimposed on a static background. The expansion itself shapes the evolution of gravitational potentials. As the universe expands, density contrasts evolve. Structures grow, but the rate of growth changes over time, especially under the influence of dark energy. This affects how quickly galaxies fall into structures and how far gravitational influence extends. At early times, when matter dominated, gravitational clustering was more efficient. At later times, as dark energy becomes dominant, the growth of structure slows. This transition influences the velocity field we observe today. So the motion of galaxies is not just a snapshot of current forces. It is the result of billions of years of evolving gravitational dynamics. Every velocity we measure carries information about initial density fluctuations, the composition of the universe, the laws governing gravity, the expansion history. This is why velocity fields are so powerful and so difficult to interpret. They encode the entire history of the universe in a subtle and indirect way. To go further, we need to be careful about something that is often taken for granted. What does it actually mean to say a galaxy is moving? In everyday physics, motion is straightforward. You measure velocity relative to a fixed background. But in cosmology, there is no absolute background. Everything is embedded in an expanding space-time described by general relativity. So motion must always be defined relative to something. In practice, cosmologists use the rest frame of the cosmic microwave background as a reference. This frame is defined by the condition that the CMB appears isotropic, no dipole anisotropy. When we say a galaxy has a peculiar velocity, we mean its velocity relative to this cosmological rest frame after subtracting the expansion. But here's the subtle point. This definition depends on how we separate expansion from motion. In general relativity, that separation is not unique. On small scales, the distinction is clear, but on very large scales, where space-time curvature and expansion interact, the decomposition becomes more model-dependent. This means that what we interpret as a bulk flow may partly depend on the coordinate system used, the assumptions built into the cosmological model, how distances are inferred from redshift. In other words, some part of what we call motion may reflect how we describe space-time, not just how galaxies are actually moving. This does not invalidate observations, but it adds a layer of interpretation that must be handled carefully. Another important factor is the role of relativistic effects in large-scale structure. At first glance, galaxy velocities, hundreds of kilometers per second, are small compared to the speed of light, so Newtonian approximations often work well. But when dealing with distances of hundreds of millions of light-years, light propagation over expanding space-time, observations tied to redshift rather than direct distance, relativistic corrections become important. For example, the redshift we measure from a galaxy is not purely due to expansion. It also includes contributions from peculiar velocity, Doppler shift, gravitational redshift from potential wells, and integrated effects along the photon's path. Separating these components is non-trivial. Small errors in this separation can lead to systematic biases in inferred velocities. Additionally, there is an effect known as relativistic light cone distortion. We do not observe galaxies as they are now, we observe them as they were when the light was emitted. This means nearby galaxies are seen in the recent past, distant galaxies are seen much earlier in cosmic history. So when we construct a velocity field across large distances, we are effectively stitching together data from different times. If the velocity field evolves over time, which it does, this can introduce apparent large-scale patterns that are not purely spatial. Again, this does not eliminate the observed flows, but it complicates their interpretation. At this point, it becomes clear that the phrase, "something is pulling galaxies," compresses a very complex set of phenomena into a simple narrative. In reality, galaxy motion emerges from the combined effect of the initial conditions set by cosmic inflation, the growth of structure through gravitational instability, the distribution of dark matter and baryonic matter, the influence of dark energy on expansion, and the geometry of space-time itself. There is no single force, no single object acting in isolation. Instead, there is a field of influence, a continuously evolving gravitational landscape. The Great Attractor, the Shapley supercluster, surrounding voids, these are all features within that landscape. They contribute to motion, but none of them alone fully determines it. This leads to an important conceptual shift. Rather than asking what is pulling galaxies, we should think in terms of flow through a structured spacetime. Galaxies follow paths determined by the global distribution of mass energy. These paths can converge, diverge, and align over large regions, producing what we interpret as coherent motion. Even with this refined understanding, there remains a fundamental limit to what we can know. Cosmology is constrained by observation. We cannot step outside the universe to view it from the outside. We cannot observe regions beyond our horizon. We cannot directly measure the full three-dimensional velocity field at all scales. Instead, we infer, we model, we compare predictions with incomplete data. This means that some questions, such as whether there exists a truly large-scale preferred direction, may never be answered with absolute certainty. They can only be constrained. Improved surveys, mapping millions of galaxies with increasing precision, are gradually reducing uncertainties. Future missions will refine distance measurements, velocity reconstructions, and large-scale maps. But even as precision improves, the fundamental challenge remains. We are trying to reconstruct a vast, dynamic system from a single vantage point using signals that have traveled for billions of years. At the deepest level, the motion of galaxies connects directly to one of the central goals of modern physics: to understand the relationship between matter, motion, and the structure of space-time. In this sense, galaxy flows are not just an astrophysical curiosity, they are a probe, a way of testing whether our current description of the universe is complete. If all observations eventually align perfectly with LCDM and general relativity, then the conclusion is clear. The apparent mystery resolves into a complex but fully understood interaction of known components. But if small discrepancies persist, and especially if they grow more significant with better data, then they may point toward new physics in gravity, subtle properties of dark matter, non-trivial behavior of dark energy, or unexpected features in the initial conditions of the universe. At present, the evidence does not decisively favor any of these possibilities, but it also does not completely rule them out. And that is what keeps the question open. One of the most subtle implications of large-scale galaxy motion is how it connects to the global geometry of the universe. In cosmology, geometry is not just about shapes. It determines how distances, angles, and trajectories behave across space-time. Within general relativity, geometry is directly tied to the distribution of mass and energy. The standard model assumes a universe that is, on large scales, spatially flat, or extremely close to it, statistically uniform, lacking any global preferred direction. Under these conditions, large-scale flows should gradually diminish as we average over bigger volumes. But if observations were to confirm persistent, coherent motion across extremely large scales, it would raise a deeper possibility: that the universe may not be perfectly described by this simple geometry. There are theoretical frameworks that allow for slight deviations: large-scale anisotropic models, inhomogeneous cosmologies, such as Lemaitre-Tolman-Bondi solutions, models with embedded large-scale gradients. In these scenarios, what appears as a flow could partly reflect underlying geometric structure, not just localized gravitational attraction. This is difficult to test directly because geometry and matter distribution are intertwined observationally. But velocity fields provide one of the few ways to probe this connection. If galaxy motion consistently points in a preferred direction beyond what structure alone can explain, it could indicate that space-time itself has a subtle directional feature. So far, evidence for such a feature remains inconclusive, but the question remains open at a fundamental level. At the same time, improvements in observational cosmology are steadily tightening constraints. Modern galaxy surveys now map the positions of millions of galaxies, revealing the cosmic web in extraordinary detail. Measurements of the cosmic microwave background have reached precision levels where tiny fluctuations, 1 part in 100,000, can be analyzed statistically. Gravitational lensing surveys trace the distribution of dark matter directly, independent of visible light. And velocity measurements, though still challenging, are becoming more refined through larger data sets and better calibration techniques. Taken together, these observations are converging toward a consistent picture. Large-scale structure follows the predictions of LCDM remarkably well. Most galaxy motions can be explained by known mass distributions. Apparent anomalies tend to shrink as data improves, though not always completely. This suggests a cautious interpretation. Rather than indicating a dramatic failure of current physics, the observed motions may represent the complex edge of an otherwise successful model. In other words, we may not be seeing something fundamentally new, but rather the limits of how precisely we can measure and model a system of enormous scale and complexity. So what, ultimately, is pulling galaxies? From a strict physical perspective, the answer is layered. At the most immediate level, galaxies move along gradients in the gravitational potential created by the distribution of matter, both visible and dark. At a larger level, these gradients are shaped by the growth of structure over billions of years, beginning with tiny fluctuations amplified through gravitational instability. At an even deeper level, the entire process unfolds within an expanding spacetime governed by general relativity, influenced by components like dark energy. And beyond that, our interpretation of motion depends on how we define reference frames, measure distances, and reconstruct velocity fields from incomplete data. So the idea of a single hidden object pulling everything is an oversimplification. The Great Attractor, the Shapley supercluster, surrounding voids, these are all real and important, but they're parts of a much larger system, not the sole cause. Galaxy motion is not driven by one force or one structure. It is the result of the entire universe acting together. What makes this question enduring is not that we lack explanations, but that every explanation leads deeper into the structure of reality itself. We begin with a simple observation. Galaxies are moving in a way that seems directional. We follow that observation into gravitational dynamics, large-scale structure, and the role of dark matter. From there, we encounter the limits of measurement, the assumptions of cosmological models, and the geometry of space-time. And at each step, the answer becomes less about a single cause and more about how all components of the universe interact across vast scales. In the end, what appears as a mystery, something pulling galaxies, turns out to be a window into how the universe organizes itself, not through isolated forces or singular objects, but through a continuous, evolving interplay of matter, energy, and spacetime. And while current physics provides a framework that explains most of what we observe, it also leaves just enough uncertainty at the largest scales to keep the question open, not as a contradiction, but as an invitation to look deeper.